My name is Nick Payton, responsible for marketing and partnerships at SigOpt, joined by Dr. Michael McCourt, responsible for research at SigOpt, and Dr. Alex Wong, responsible for chief scientist at DarwinAI, as well as chair of the VIP lab at the University of Waterloo, among many other titles. Tiffany is going to post their biographies in the chat, so you have full information on both of them. At the same time, we'll start this presentation with a quick introduction from each of them, so they can explain in a little bit more detail their background and how they came to the place where they both contributed, in the case of Dr. Wong, in developing COVIDnet itself, and in the case of Dr. McCourt, in tuning some of the free parameters for the model itself. So to give you an quick introduction to today, we will be talking about COVIDnet and discussing, a lot of the aspects that went into the model itself, some design decisions, the way that the hyperparameter tuning process was set up, and then talk through some of the real world impact that it's had, as well as some of the things that you could do to potentially contribute, and some of what we're looking forward to going forward with the model itself. In terms of participating today, please use the Q&A functionality within Zoom to ask any questions. I know a lot of questions will be pertinent to the particular section that we're on at any point in time, so I will be moderating that vigorously, and we'll surface questions directly to our presenters as they're going through the conversation. If you have any other issues, feel free to chat me directly, and I'll try to address them as quickly as possible. But without further ado, I'll kick it off to Dr. Michael McCourt, and we'll go forward from here.
Yes, thank you very much, Nick. I am very excited to be here today and to be able to talk about a project that I'm very excited about. At SigOpt, we have a product that can serve a lot of purposes. It can help a lot of different projects. And this project in particular, I find extremely exciting, not just from it being a very timely project, but also something that could have a very significant impact outside of just the world of tech. And in particular, when I heard about what was going on here, I said that this is something that's very exciting that really needs our attention and our support. Dr. Wong, I'm wondering, can you explain first off what the VIP lab is and also what DarwinAI lab is?
Sure, and not a problem. So thank you. So just a quick description. So the Vision and Image Processing Research Group is one of our research groups at the University of Waterloo that I'm a director of. We have around 50 to 60 different research personnel working on all sorts of different facets for enabling operational artificial intelligence across different industries. So that has been the main focus. And because of the, the scholarship and research that we've been doing that's really industry friendly, there's been a number of spin-offs from our research group, one of which is DarwinAI, which I'm one of the co-founders. And the focus of DarwinAI has been building a deep learning development platform that enables AI-assisted deep learning development workflows to allow people to hit operational targets faster and create networks faster.
Excellent, excellent. What then is the continuing relationship between Darwin and the VIP lab? Are you constantly able to engage students in this industrial perspective?
Yes, no, that's a very good question. And the answer is yes, because of, our close-knit relationship with industry, with different industrial partners, the ideas that we have at the Vision and Image Processing Research Group becomes very guided by solving some of these fundamental problems that we hear from industry, that they see there's a big need, especially in the realm of machine learning, deep learning. And a lot of those ideas then gets fleshed out into fruition from a commercialization perspective through DarwinAI, which then allows us to enhance our deep learning development toolkit and platform to address these particular needs. So it's really intermingled, and it has been very important for us to really try to give people something that they can really use from an industrial perspective.
Excellent, excellent. It's very, very interesting, and I'm personally very excited to see not only a strong collaboration between academics and industry, but also the evolution of projects and teams that have started at a university, then going on to become successful in the industry.
Completely agree with you.
That's something that, but please.
Oh, yes. Oh, I agree. I was just saying that I completely agree with you. And that's where the mentality of turning, I guess, research into tangible reality to help industry, as well as, I guess, help society becomes very important. And that's also why we started the whole COVIDnet project as well.
Yes, yes. And let's move on. Let's talk about the COVIDnet project now. First off, can you describe what led you to say, we need to work on this, we need to develop tools to help address these problems?
So let's start. So one of our key driving factors is, first of all, I've been, I guess, doing medical imaging research, especially AI-assisted clinical decision support and workflows for the past 2 decades now. And so when we saw the current pandemic happening, what we try to do is think, what are some of the key ways that we could try to contribute back to society in a way that AI expertise really allows for? And so one of the key things that we noticed is that when people undergo COVID-19 screening, I guess RT-PCR, tests, so the viral testing is a very crucial gold standard for it. But what also often happens at the same time is chest radiography is done, mainly because with viral testing, there's a lag time before you actually get results back. And so you need to figure out, what do I do with the patient right now? Do I send them home? Do they stay? What kind of treatment do you give them? And you just don't want to really wait. And the other key thing is that what viral testing don't really provide necessarily is how severe a condition is. And that's actually critical for treatment as well as triaging and individualized care. So what we see is that in a lot of hospitals worldwide, what they do is they do the viral testing with RT-PCR, and they also do chest radiography at the same time. So given the fact that chest radiography exists already and it's part of standard practice, can we actually leverage AI to help clinicians, help them make better decisions faster, so people can be treated quicker, they could plan better, so on and so forth. And that's kind of the impetus of why we started looking into the whole COVIDnet project, mainly because with our expertise in AI, deep learning, and our knowledge of the medical space, can we combine the two to create something that would be useful and impactful for, I guess, society?
Fantastic, and that's just a really exciting for me opportunity, but also an insight from you guys to be able to say, hey, here's a chance for us to leverage the tools and tech for something that can have an immediate impact. Maybe we can talk now about what the project actually is. How is it that you are considering these radiology, the opportunity here for the radiologists to be able to make this contribution?
Yeah, no, that's perfect. So essentially the COVIDnet, I guess, initiative is a global initiative that we've launched that is focused on open access, open source deep learning for detection of COVID-19, as well as risk stratification of COVID-19 based on chest x-rays, so chest radiography. So the key problem that we have right now is, based on x-ray images that are captured of a particular patient, can we actually differentiate it between, let's say, other types of conditions, for example, non-COVID related pneumonia, things like non-COVID viral pneumonia, bacterial pneumonia, and other forms of pneumonia, or even just from other types of conditions from the characteristics of COVID-19 detection. And so if you take a look at this particular slide right there, what you see is that the differences from a visual perspective between what a pneumonia infection that's not caused by COVID and one that's caused by COVID is actually quite subtle. And so the ability to build deep learning, AI that's able to identify, learn, and extract these visual markers for differentiating the difference becomes actually quite important to help radiologists discern these really subtle signs. And so that's been the main focus of the project. And so what we've done is we provided both continuous updates on reference models, which we call COVIDnets, over time as more data comes in. So clinicians, researchers, or just citizen scientists can take and make use of it and build upon it. And we also provide the underlying data so that they can actually expand upon it.
That is also a really great part of this. Not only the fact that the data here is open, the development process has been open and is all on GitHub, but also this collaborative sense of things. And that's something I'd like you to talk about briefly now. We could talk about more later as well, is the collaborative element of this with physicians.
Yes, that's exactly it. And so this has gotten a lot of, I guess, worldwide attention, as well as the most important global support from from clinicians as well as clinical institutes. And so we've been talking to different hospitals from around the world who has expressed interest, and some of them are,
We may have a bit of a technical difficulty here.
Yeah, I think, Dr. Wong, I think we might have lost you for a second. So, which happens. This is the world of all of us working from either home or wherever we're most safe. So I think once you get signal back, we can pick back up on how you work with physicians. In the meantime, we've gotten a couple questions.
And one
question,
happy.
I think Dr. Wong, once you're back, one question actually speaks directly to what you were referring to on how you're working with physicians directly. So the first question is a lead-in. Can you hear me again, Dr. Wong? Just to confirm.
Dr. Wong,
Hello, can you hear me?
Yep. Yep, we can hear you. We have a question.
Sorry about that.
It's fine. We have a question that leads into this discussion of how you're working with physicians that I'd like to ask so that you can get back into that line of discussion around how you're collaborating. What features are radiologists looking for in differentiating these two x-rays? Does this match with the features that the model prioritizes? So I think complete your thought, obviously, first on how you're collaborating with physicians, but then potentially lead into that direction so we can discuss a little bit more around the model design, I think is where that question is largely leading.
Perhaps Dr. Wong may be on mute now.
He might have frozen.
Yes, can you hear me clearly? I just want to make sure.
Yes, sir. Yes,
yeah.
Okay, perfect.
It's
Sorry about
easier.
that. Just technical.
Yeah, I was going to say it might be easier to cut video too, which is fine as well. Yeah.
Yes, so I'm just going to do that. So a very good question. So one of the key things that we're collaborating with, I guess, clinicians around the world is we would have essentially a regular, feedback that they would give on some of the stuff that we're doing, as well as talking to them and trying to really figure out what are the key pain points and challenges for not only that they need to make proper planning diagnosis as well as risk stratification, but also figure out exactly in what form do they need to see it in. So one of the key things with clinicians is that at the end of the day, a clinician is wonderful at what they're doing, but they're not machine learning scientists or AI scientists. So delivering this in a form that they could use it and get feedback and get, screening information, risk scoring, and so on and so forth, in a way that is understandable from a clinical perspective becomes actually quite important. And so the other question that was asked was related to what are some of the signs that radiologists are looking at? So the signs that the radiologists are looking at, if you go back to the example that we have, is they're looking at something, could be subtle at the early stages, but they're looking for things like ground glass opacities, as well as infiltrates. So these can usually be noticed based on the opacity within the lung. So there are certain areas where it doesn't look as clear as you would usually see, and the geographic extent of it, as well as how opaque it becomes, are some of the key indicators that they're looking at. And related to what are some of the signs that the models identify, I'll talk a bit more about that later on during how we actually do our model validation to make sure it's actually looking at making right decisions for the right reasons. And you'll see that it's able to kind of identify these similar kind of features that a radiologist is looking at.
That's a very good point. I guess this is then a very good time to also jump from a discussion of the problem to strategy for trying to address the problem. Maybe you could spend a little bit here talking about the design of the network, the research behind it, how the architecture, data set, parameters, training sort of evolved over time to best address the status of the modeling problem.
Sure, I'm just going to do that right now. So just on a high level, what we did was one of our main research questions was how do we actually really rapidly develop deep learning, deep neural networks, especially in a case where the urgency is quite high, such as for the COVID-19 pandemic. And so the key approach that we took was the human-machine collaborative design approach, where what we did was we collaborated with AI. So we treat AI as a collaborator that we work together to achieve a certain level of operational requirements, so operational targets. In this case, making sure it's sensitive enough, as well as has good specificity enough that can be used for clinical purposes. And so just a really quick summary of what we did. So the first step was us as developers was what we looked at was what is the underlying scaffolding that we want to do to achieve our goal. And that first step is what we call the human-driven design prototyping stage, where we created a rough model prototype for the data. Then in the next step, what we call is the machine-driven design exploration approach. That's where we leverage DarwinAI's GenSynth platform, where we took the prototype, we took the data at hand. In this case, it's the COVID data, as well as we also specify some operational requirements, so operational targets. And so based on those, we then fed that into GenSynth for it to learn and automatically generate models that meet those particular operational requirements, and as well as leverage the GenSynth platform because it learns the ability to create networks. It's also able to explain it. And so that's where the auto model generation and auto model explainability comes in. Can you go to the next slide? Perfect. So here's just some additional details. So as a starting point, what we did was first we had to amass data. And this is something that's actually not too trivial given I guess, sparsity of some of the data available for training something like this. So what we did was we had to look at different sources of data ranging from the RSNA to the COIN dataset, to some of the other sources that we work with partners to make publicly available. And so we're able to essentially create what we call COVIDx, which is a data set of over 13,000 chest x-ray images that are annotated and can be made available to the public for developing these models. So that's our very first step. Can you go to the next slide? So then given this information, so given this data set, and given the general model prototype that we created, which is more like a residual style prototype, as well as requirements of making sure that sensitivity as well as PPV are above 80%, then we fed all that into GenSynth for it to learn and create new models. And so this is the model that it ended up generating. So it generated the macro architecture design as well as the micro architecture design. And so what we end up with something is actually quite interesting in how it's able to find a good balance between efficiency as well as accuracy. And so what you see from this architecture are a couple of interesting points. One is that you'll see there's actually a very high architectural diversity. So it's actually quite tailored for this particular task of COVID-19 detection. The other key things you'll see is that it was able to create a brand new type of module, which we call a PEPX module design pattern that's largely comprised of point-wise convolutions as well as depth-wise convolutions, which are very quick from a calculation perspective, so low computational complexity, but this particular combination allows it to have high representational power. And the last thing I'm going to mention that's interesting is that it has a very interesting selective long-range connectivity design. So usually when you look at residual architectures, they're usually short-range connections. So there's short-range skip connections. Here what it did was GenSynth designed something that was quite unique in the fact that there's these very long-range connectivity to allow information to better propagate for better training and representational power. But you'll see that they're centralized on these point-wise convolutional hubs. In which case this also reduces the amount of information that needs to be sent, as well the amount of processing that needs to be done. And it just shows that taking this human-machine collaborative approach becomes actually very interesting for getting something that as a person or as AI alone would not be able to achieve, but the synergy becomes something that's much better. Next. Perfect. And so we were able to first of all, once we've actually developed the models, one of the key things that we need to do is performance validation. And so we do it in two different ways. One is more your standard quantitative performance analytics. So here what you see is the confusion matrix that we got for COVIDnet. It's actually quite good. And the most important thing for us, less about the actual overall test accuracy. What's more important from a clinical perspective is COVID-19 sensitivity as well as positive predictive value, which is sensitivity, does it actually detect the COVID cases? And in terms of positive predictive value is great. For the ones they actually do say it's COVID, are they actually COVID? And so fortunately for us, we're able to achieve a pretty high sensitivity, but more importantly, very high positive predictive value so that it doesn't lead to too many false positives, which could add to the burden from a clinical perspective. And this shows how taking this human-machine collaborative design approach allows us to build a COVIDnet architecture that allows us to outperform some of the other ones while being orders of magnitude faster as well as requiring less memory, as you can see from table 1. So we're actually quite happy about that.
And Dr. Wong, there were actually two questions related to results, or I guess at this point, two clarifications, just to be clear on the questions that were asked well before you presented these results. The first is, does the model provide better results than human for X-ray analysis?
So that's a big question. Does it provide better? So right now, that study that is ongoing, that's actually, we haven't confirmed that. So right now, all these results are confirmed based on RT-PCR tests. So in which case, based on the viral test, they say, this is COVID, this isn't COVID. And so that's what we verified against. So how well a radiologist does, that's actually one of the exciting studies that we are exploring next.
That's great. And then the second question, do radiologists still have to interpret images assessed by COVIDnet? And if so, then what benefit does COVIDnet provide to clinicians around either speed, second opinion, something similar?
So a very good question. So the answer is yes, human interpretation becomes still very important. It's something that we're working with, but one of the key things is that once, let's say, it says it's positive. For me, from having worked with clinicians, and I've actually worked at a hospital before, having human in the loop is very key for confirmation. So that's almost a must. Then the question related is, okay, if a person needs to look at it anyways, what's the added value, right? So one of the things I like to say is, one is it provides first of all, a second opinion. That's one. The other key thing is that because of the overwhelming number of cases that needs to be looked at, it's not often the case where a expert radiologist would be able to screen through so many. And that's been happening in a lot of different countries right now. A radiologist just cannot go through this massive amount of information. So what this utility, something like COVIDnet provides, is it enables other frontline workers to be able to quickly get a good assessment or understanding while waiting for viral testing and so on and so forth, so that they can make a better decision now, because there's an urgency to it, and making a snap decision that's guided by data becomes very important. So the short answer is expert radiologists would be ideal. But one of the key things is that it's just, there's not enough radiologists out there to be able to look at all cases. And if we're able to even help frontline workers make a quicker decision in a informed and reliable way, I think that's where the utility comes in.
That's great. Thanks for clarifying both of those points. There are actually two other questions while you were answering those two that came in related back to the data set itself. The first is, how big is it? And the second is, what are the criteria to select or not select images from public data sets? And how is that decision-making process made?
Okay, now that's a very good question. So the first part is how much is there? There's around a little over 13,000 chest X-ray images of a variety, both of different types of pneumonias, as well as healthy, as well as COVID. Because as you know, with deep learning, machine learning, having diversity and variety becomes quite important. And the other key thing is that from a demographic perspective, we actually have another study. It's actually from all across all the different continents, which is actually very important to account for any kind of demographic diversity. So that's the first question. And so can you repeat the second question?
Yeah, of course. The second question is, what are the criteria for selecting or not selecting images from public data sets to, I guess, expand potentially the data set that you have available for training the model?
So that's a good question. So just essentially, it's a two-part question. One is, given particular data sets, we always do the usual split, so we have random splits. So that's the usual way of doing training, testing, and so on and so forth. There's no specific criteria for that. And that's just to make sure that we don't add any human bias into it. In terms of the actual different data sources, that becomes quite important. Our selection criteria is, while subjective, it's based around quality, and quality becomes important. So for example, there were certain sources available that we looked at. They were, for example, chest x-rays that were captured off of a computer screen where there's a reflection of, let's say, I kid you not, flowers and people in the background. So clearly that's a good indicator where it's not particularly useful. We've also looked at some of the quality of the sources. So for example, one of the data sets we used was from Mila in Montreal, a pretty well-respected institute. With a lot of the pneumonia cases, they come from the Radiological Society of North America, in which case from a reputation perspective, we know that it's high quality data.
That's great. Thanks for that clarification and for expanding on both fronts. I think that's really an important distinction. We actually, and questions just keep coming and they're good ones. So I want to keep going on this front. This one might even be a lead into a discussion around some of the tuning that was done as well. When looking at the architecture, in your opinion, Dr. Wong, how can you improve the performance? They asked, around fine-tuning the architecture in order to improve the performance. You could think about manual tuning or using intuition from an expert. Just looking at, and how do you think about boosting the performance of the architecture itself?
That's a very good question. So there's been a lot of different schools of thought in terms of how best to improve the underlying architecture. And if you actually look at the, development cycle for a lot of deployable deep learning, a massive amount of time is actually spent on actual architecture tuning itself. A lot of standard practice right now, because of the the maturity of deep learning right now, has been a lot of hand tuning and so on and so forth. And I definitely believe in human intuition. We use that a lot. But for me, again, I'm more in the camp of human-machine collaboration. So me as a human can have a high-level picture of the scaffolding that would make for a good network, but one that is optimal and tailored to task is not something that I feel, after like 2 decades of experience, I'm able to do to its fullest fruition. And so that's where the machine-driven design exploration comes in. And that's why we leverage DarwinAI's GenSynth, which I partly created the IP behind, which is, given human intuition, given the scaffolding behind it, the prototype behind it, the data behind it, as well as the thing that's most important from a human perspective, the human-driven operational requirements and targets. Can we have AI learn from it to build better tailored architectures. And that's the approach that we took here. And as you can see from the results, it actually works very well in terms of meeting all the, in this case, exceeding your operational requirements, both from an accuracy perspective to a architecture efficiency and capacity perspective. So for me, the human plus machine-driven approach is the best way to go.
That sounds great. There was one other question that came in. It relates a little bit more to the potential real-world impact and alternatives to looking at X-rays. So I'm going to actually take that question and leave it for you to answer once we get into some of the impact itself.
Sure, that sounds good.
For the listeners there, just know that we'll get to that question as well. It's a very good couple questions that can tee that section up pretty well. So I think at this point, it'd be great. Yep, go ahead. Sorry.
What I'm just gonna, I'll wrap up and then I'll, I guess, according to Mike's hands. So what I'm gonna do right now is, as the very last step, now that we actually have quantitative performance analysis, is the explainability-driven analysis. So there are many situations where your numbers look great, and then you end up with a result that's completely unusable. And I know this because we actually had this experience when building COVIDnet. So we had something that has really, really high sensitivity. And then we looked at it using explainability. And then what we realized was the model was having these great decisions because it was reading symbols from the chest x-rays. Or another funny story was we were doing it for CT scans, and it got 100% sensitivity because it was able to magically identify the beds that patients were lying on. So these are definitely situations where the model is making the right decision for the wrong reason. So as our very last step, once we have a model, what we do is then we do explainability-driven analysis so we can have a better understanding in the critical factors that are used to make decisions. So in this particular case, we use GenSynth, particularly the GSInq approach. These are some of the areas that we saw that were critical factors. And it was great because it was actually looking at infiltrates. It was actually looking at ground glass opacities. And I mean, even just the fact that it's actually looking inside the lung is actually a very reassuring thing to make sure it's not looking at text or background kind of cues. And then the other key thing that was interesting was that it was also, by identifying critical factors, it also allows us to help radiologists potentially get new insights that they might not have noticed that the machine, that the deep neural network was able to see. So that's pretty much our general steps in design into making it happen. Then we released it into the wild. Great collaboration with Michael at SigOpt to look at the additional things that we could to improve it through tunings and augmentation.
I think we might have lost Dr. Wong for a second there on audio, but this might be a good time.
Hello, can you hear me?
Oh, yep. Hi. Yes, we can hear you now.
Hi.
We lost you toward the end. We caught most of the explainability-driven analysis piece. Just toward the end, as you were speaking about, I think some of the work that you collaborated with Mike on.
Yes, so I'm just going to finish that and then I'll let Mike continue. So that's where we have our nice collaboration with our friends at SigOpt with Mike, where decided to look at, are there ways to further boost the accuracy by looking at some of the free parameters associated with data augmentation.
And thank you very much for the handoff, Dr. Wong, and also for your very helpful answering those questions, topics which I also am very excited about and would like to learn more about. In particular, on the tuning front, our goal here is to take decisions which are very hard to make in a vacuum decisions about things such as learning rate, or decisions around data augmentation parameters, and try to make them both effectively but also efficiently in the context of metrics which are of relevance in the specific project which we're studying. First thing I'd like to do is quickly just give a brief introduction to SigOpt. And in reality, SigOpt's goal is to serve a very black box purpose with the intent of being able to work on a variety of different problems very naturally. And you can see there on the left-hand side, data, models, testing exists separately from SigOpt, which allows it to work in a variety of computer vision problems, but also natural language processing problems, classification, reinforcement learning, or other projects which have nothing to do perhaps with machine learning. In this particular project, we were interested in using SigOpt to understand to some degree how the data augmentation process went. And in particular for this project in data augmentation, what the real issue is that there's a very small number of samples of COVID-19 in the data set, of course, because we're still gathering more samples. The whole process is very much in flux. I think on the next slide, we have some specific numbers, maybe 14,000, yeah, there it is, 14,000 non-COVID examples. And that's, of course, even down from the huge number that Darwin could be using in this process, but is cutting down on for the reasons he'd already mentioned, making sure that they're very high quality, trustworthy examples. So as a result, Darwin, and in particular, I'd like to call out here Linda Wong, who is at the VIP lab at University of Waterloo and also collaborates with the Darwin crew. She has helped bring us into the mix here to help think about the implications of the data augmentation process, which is to say that as the training proceeds during each batch, as they're being fed into the stochastic gradient descent process, certain examples are added which are known to be COVID-19 positive. However, because there's only 183 such examples, it's very hard then to do this in a principled fashion without some amount of overfitting, which is exactly what Dr. Wong was alluding to before, where the model can learn something which isn't actually generalizable, such as which bed somebody is laying in. So we decided to study 4 specific parameters during this data augmentation process. And basically what's happening in the data augmentation process is that each image, each COVID image, is being manipulated and altered in some way to help it represent some other COVID image that we haven't yet been able to see, but hopefully we still want to learn from. And we basically, what happens is we take the image and maybe zoom in a little bit, translate the image a little bit so that the lungs appear maybe slightly up and to the left or down and to the right, rotate the image somewhat, and account for the brightness of the image as well. The trimming process actually was something that was fixed essentially at the start of this. We considered tuning this, but Linda identified that by cutting off the top 1/6 of the image, a good deal of the necessary trimming could already be done. So that was something that didn't end up actually tuning. On the next slide, you'll see here that we reference, and in particular, I want to give another shout out to Olivia Kim, one of my colleagues here at SigOpt. Olivia helped me with a good deal of the technical details. And in fact, Olivia and Linda worked for a while to make sure that all of this ran within the cloud framework and also ran under the specifications that were most up to date at the time when we ran this tuning process. And Linda helped identify the key parameters that we wanted to study, in particular, as I mentioned, the 4 data augmentation parameters, the choice of the loss function, and then 2 of the training parameters, the learning rate and the batch size. And we can see the results of this tuning process on the next slide here, which is demonstration of the competitive nature of these metrics, as Dr. Wong described before. You can see here on the left a plot that demonstrates both the PPV value and the sensitivity value. Now, if our goal were to minimize false positives, we'd want a very high PPV value. And if our goal was to minimize false negatives, we'd want a very high sensitivity value. So in reality, we want both. of course, one, very low false negatives, very low false positives, but they are competitive metrics. You can do very, very well at one by doing very, very, very bad at the other, as indicated in the top left portion of that graph there. So in reality, we wanted to somewhat explore not just the competitive nature of these metrics, but also which parameters are most relevant in making sure that you identify these highest performing outcomes, and in particular, highest performing in terms of both high PPV and high sensitivity. And you can see there a circle in the red circle, the result that has this highest sensitivity value subject to a suitably high PPV value. And if we go to the next slide, we can actually see this graphic that represents how the different parameters in this highest performing region, which you can see subset there to the right, how these parameters were localized in specific regions of the entire search space. And in particular, the metrics of study were in the first two columns, and the remaining columns are all the parameters. Certain parameters really had to be set a specific way. Batch size, learning rate had to be set a very specific region. Some of the parameters, brightness, and in particular this class weighting, which is this impact on this loss function, as we mentioned earlier, it had much less impact, which could be a function of any number of different things. More study would have to be conducted. But in particular of interest, or at least a surprise to myself and Linda, was that the rotation and translation parameters did have a very specific, what I'll call maybe the sweet spot, the region where adding additional augmented images with a somewhat high rotation, and actually what in my mind is actually a pretty solidly high translation, can provide the kind of high performance that it is that we're looking for. And the hope is that we can do some further investigation, understand what the implications of this is, and see how this can be used in future projects as well, because clearly they had a significant impact on the performance of this particular project. At this point, I'd like to throw it back to you, Nick.
Yeah, that's great. Thanks, Mike. I wouldn't be a good marketer if I didn't make it clear that all of those visualizations that Mike was showing were directly from our dashboard in SigOpt as well. So not only the API to tune the hyperparameters and run the process automatically and efficiently, but the dashboard as well. I think now there were a couple questions that might be a good lead into discussion of impact, but I think we'd love to start with a discussion that goes back and forth between both Dr. McCourt and Dr. Wong on real world impact and some of the research impact of this. So looking at it from a couple different angles. And I think kicking it off, Dr. Wong, if you're available to discuss right now, there were two questions that were directed at you from a self-described big fan of yours. So you have fans in the audience, just to be clear. The first question is, will there be a domain shift problem if you want to test or train model to a developing country like India, as an example, where possibly the image quality can be different? And do you have any plan to collect the data from different countries? I think you might have spoken to this a little bit, but it'd be great to revisit that as a way to kick off this discussion around impact. And I'll advance to the next slide as well. Actually,
sure.
This is just pure discussion. Sorry, I'll keep it here. But
yeah,
Dr.
sure.
Wong, if you're available.
No
yeah,
problem.
That's the first question. Yeah.
So I'm just going to answer that very first question. The answer is that with any kind of machine learning, deep learning scenario, there's always the potential for domain shift, where you might have different quality of information. You might have, for example, different machines being used. It's actually quite common. And there's been a number of studies that has been undergone where sometimes it might even show some bias towards a particular make and model of a particular imaging equipment or a particular protocol. And so the answer to that is that could happen. And that's why we've tried to diversify the data sources. So for example, with the data sources, one thing I didn't get into too much details was we try to make sure that not only is it from different countries. So we mentioned, we have the data from, let's say, from Asia, from Europe, from Middle East, from North America, so on and so forth. But we also have ones that are taken under different protocols. Some of them are supine, some of them are standing up, some of them are from fixed, I guess, high quality systems. We also have ones from portable systems, as well as ones with different protocols. So you have posterior interior views and interior posterior views. So the hope is that by having this diversification, it allows us to have a more generalizable model that is unlikely to see as much of a domain shift. But as you can see, we're continuing to improve the models as well as data, and we're making all that available so that we could then continue to build up, and hopefully these problems might go away. And then the last thing that I'm going to mention is that in the situation where something might be too diverse, we've also talked to different clinicians where they're able to then customize it for their particular demographic. So for example, in the I guess the question that is asked for, let's say, a developed country, maybe really customize it from the data from that particular source might be a good solution. Those are different areas that we're trying to explore. So essentially one solution, we're trying to make it as generalizable as possible. The next one is we're giving it open source and available so people can then customize it for their particular scenario.
That makes a lot of sense. Thanks for that. Another one getting a little bit closer to kind of real world impact of the model itself. This individual is reading that X-ray is potentially not the most widely used technique for COVID detection from a clinical perspective. And if you could comment on that, shed light on that, explain how it fits in to the extent that that you have depth on that subject, I think that could be potentially helpful context as well.
Sure, no problem. So that's a very good question. So in most, at least in the early days of COVID, from a guidelines perspective, chest radiography is not an approach that you would recommend for exclusion, as in you would not use it to say somebody does not have COVID. But chest X-rays is still very regularly used right now for severity analysis, as well as for a particularly portable photography as a complementary tool to existing protocols that use for COVID screening.
Great. Do you mind just repeating the last minute or so of that explanation? You broke up just a tiny bit, and I think that could add a little bit more additional context there. If you're available, which may not be the case.
Yes. Can you hear me?
Oh yes, yes. If you could actually just explain the last bit about how X-rays fit in alongside other methods, I think that would be helpful for answering that question. Yeah.
No problem. So there's been a large number, there's actually been quite a few recent studies that has actually advocated the use of chest X-rays for handling COVID-19 cases in a number of different scenarios. So for example, one is for severity assessment, as well as monitoring of individuals who are more in the critical illness area, because that's where viral testing no longer really gives you good information about. The other thing is that there's a lot of situations where, especially in developing countries, where they have a short supply of viral testing. And that's where chest X-rays can also be very beneficial. And last but not least, in a number of different studies, they're kind of advocating the use of portable chest X-rays, because these are situations where in the in the early stages, they're saying, okay, great, we would actually bring somebody into, let's say, a CT room or a standard X-ray room, and that actually can lead to a greater spread of the infection, especially, and it takes a long time to actually do decontamination. By using portable chest X-rays, they can actually bring it directly to the patient, and leads to much mitigating the risk of infection, as well as also making it easier to acquire without having the patient having to enter the hospital system and enter the room. So also for a very fast decontamination. So those are some of the scenarios that are being used right now. And again, the other key thing is from even in the situation where there's viral testing, the chest X-ray is usually there as a complementary technology. So you would screen using both while you're waiting for your your viral testing results. You could use the chest X-ray results to kind of identify how you should manage the patient. Maybe it's okay, so then they could go home and wait for the viral testing results. Or if it looks severe enough, that they would stay and wait for the results while being treated.
That's great. Thanks for that. One follow-up comment, not a question, from an attendee is it seems that rapid identification of chest X-ray could enable clinicians to isolate patients more quickly while waiting for their diagnostics, which is, a nice summary of a lot of what you were speaking to as well, in some context. Another question that I think is a little bit closer to the research side, and looking at model design, is whether the architecture search was validated on the test set or the training set, and question around how validation happened through the training and the tuning process as well.
That's a very good question. So as part of it, with GenSynth, what you do is you provide the training information as well as testing information. And then what it does is it iterates through and tries to get a deeper understanding based on the training data. So that it has a better understanding. So part of the training is being kind of siphoned for that particular purpose. And then all our final results are based on the test set.
Great. And then speaking of GenSynth, there was an additional question on how it worked. The explainability feature in particular, if you could explain how you can find those important regions that you showed in the image with the platform. That would be helpful.
Sure, I'll just give a very high-level summary of how GenSynth works, and then I'll kind of say where the explainability comes from. So the way GenSynth works, so full name is like generative synthesis, is based on the interplay between two different entities. One is a generator entity, the other one is a inquisitor entity. So the generator is responsible for generating neural networks, and it learns to do it better and better by taking advice from the inquisitor. And so the inquisitor itself is responsible for looking at these generated neural networks and seeing how information goes through them to see how the network behaves, and then coming with a good picture into the inner workings of the neural network so that it can then provide advice to the generator to do better. Say, hey, this one's great, but these are areas that you should improve upon. And so this interplay keeps going in a cyclical manner until one gets much better at generating neural networks for satisfying operational targets, while the other one gets very good at being able to explain the inner workings of neural networks. And so that's essentially how it's able to generate these models. And so where does explainability come in? Well, the inquisitor, in learning more and more about how to better explain the inner workings of a neural network, can then transform that information into something that is viewable. So in which case it transforms it back to the original domain, in which case that's where the critical factors in the original domain can surface up.
That's helpful. I know that we're short on time, so what I would love to do is give you, Dr. Wong, and you, Dr. McCourt, both an opportunity to give any closing remarks you want on impact, either on the real world side or the research side, and then I'll wrap it up from there.
Dr. Wong, if you care to go first, please.
I'll keep it brief, both on the research side as well as real world impact, and then I'll give more time for Mike to give us some additional insights. So from a research perspective, I think what's important for us from a research perspective is being able to kind of identify what kind of architectures are good for a particular kind of test. In this case, for more of a medical clinical decision support. And the other key thing is also from a research perspective, really seeing what kind of critical factors that neural networks actually leverage in making proper decisions for clinical decision support. And so for me, that's the key research impact that's important. From a real world impact, it's pretty much having something that's available to the world that they can build upon, improve upon, and hopefully hopefully get to the stage where it has a real clinical impact. That's essentially the vision and dream that I have, that everyone would be able to leverage this to, I guess, help with this current situation.
That is, yeah, that's the dream. I totally agree with that. And in the case of SigOpt and how we've been considering this from the data augmentation perspective, I think that my sense of the impact here is trying to identify what aspects of data augmentation are most relevant in this project, but then also more broadly, how are insights from that transferable to future projects, or actually projects in another field? We've been recently working on some projects actually in additive manufacturing, which don't specifically require data augmentation in this context, but do benefit from the same strategy, the same mechanism, and learning from here what limitations there are in the data and how to overcome them through data augmentation have helped already in another project, and I expect will be able to help elsewhere. I think additionally, speaking to some of the complications of the artifacts of getting data from various different sources of different quality data that Dr. Wong has already spoken to, that there is a great opportunity here for us to take what we've learned and provide that to the community and make sure that people who are going to take this and use it understand the opportunities that are present and also the circumstances under which it was created. And that's one thing I really love about the COVIDnet project, is that it's totally open. And DarwinAI and the VIP lab have done a really fantastic job documenting and putting forth all the information regarding how this has been created. And I'm just very excited about it.
And I'll echo a comment. I'll leave us with a comment from the audience on how critical this work is, and offer to thank you. So thank you both for your work on this important project. And thanks, Dr. Wong, for joining us. And thanks, Dr. McCourt, for your time as well. I'd love to leave us with a couple ways for people to engage. You know, you can go to Darwin's website, get access to their success stories, get access to a demo, and learn about how you could potentially use the product. You can do the same at SigOpt. In particular, we wanted to highlight, we have enterprise projects, enterprise version of our product, but we also have one for any research that you're doing in academia where you plan to publish. You can use SigOpt for free. So highlighting that here, just go to sigopt.com/edu. You can access the SigOpt experiment. It's a public link here as well, and we'll make sure that we provide that to anyone who's interested. And most importantly, you can contribute labeled data to this project by following this link. We'll make sure that you have that link available in the follow-up email as well. But you know, that's probably the most important of all of these different things that you could potentially do related to this project. So without further ado, I want to thank both of you for joining us today. I really appreciate you sharing the time and sharing your insights on this important project. And thanks to everyone for joining us as well.
Take care. Have a great day.
Bye. Thank you.